Assalamualaikum everyone. Sheikh Hani, how are you? Can you hear me all?
Yes.
Okay. Yes, so Auzubillahi minash shaitanir rajim. Bismillahir Rahmanir Rahim. Assalamu alaikum wa rahmatullahi wa barakatuhu. Good morning. Sabah al khair. Can we start, or we would like to wait for a while? Good.
So there are So there are 10 to 15 students. We can wait for 5 minutes.
Okay. You know, you are the last one holding the fort. And in Pakistan, we generally give the highest medal, which is called Nishan-e-Haider, to the people who hold the fort. Uh, it is often given after Shahadat, but I don't really want this thing to happen with you, right? I want all of you to survive, thrive, and excel. Where is Yahya and Amina? So I want everyone to come in the front rows. Here we have Yahya, and Amina is missing also. And okay, so
His Excellency ICCBS जो कराची है उन्होंने भी आपको माइक ऑन किया हुआ है तो अगर आप उन्हें कह दें कि वो आपको म्यूट कर दें तो इको नहीं आए
हमारा my IT staff is saying something. आप बता दें.
अस्सलाम वालेकुम मैडम आपका माइक ऑन है तो काइंडली इसको ऑफ कर दीजिए आप उसी वक्त इसको ऑन करेंगी जिस वक्त सर आपको कहेंगे
ठीक है। So we can start now.
Thank you very much, madam. Thank you for your instruction. Okay, so Assalamu alaikum again, and this time from Islamabad. This is a beautiful chilly weather. It is about 16 degrees centigrade and sunny and beautiful. I am in my office, which is just in front of Prime Minister's Secretariat and also the Supreme Court of Pakistan. Okay, so what we intend to do is to just in the first few minutes, inshallah, we'll try to re-explain polarization transfer just for the sake of completion, because I know it's important that we keep tracking of what we have already studied. And I wish to remind you that we are discussing a very important problem in NMR spectroscopy, and that is sensitivity. I told you that sensitivity is a major issue, and that a lot of work in the initial few decades have been focused on improving the sensitivity of NMR spectroscopy. And there were many very important developments made. And I give you a brief list of what has happened. Very high field magnets were developed. Now, currently, there is an NMR machine which is available of 1200 megahertz, means 1.2 gigahertz. And that machine is now installed at 3 different places in the world, including the University of Ohio Arts and Science College, where this university, Ohio State University, where this machine was the first one to be installed. This is only 17.5 million USD, and you know exactly well that with the superconducting magnet, when you have a stronger magnet, you have larger energy difference. When you have larger energy difference, you have more population difference. You also know that B naught, which is the applied magnetic field, your strong magnet, is directly proportional to Larmor frequency. So it certainly, a stronger magnet help you to improve the sensitivity of NMR experiments, particularly for the people who are working in the field of structural biology, which work on very large molecules and also in very small quantities of sample. For them, it's not possible to get the structures of the biomolecules on small, uh, on weaker machines such as 300 or 400. They generally start their work from 600, move onward to 800, and sometimes 1000. I also told you that cryoprobe technology, which is now, we have been using cryoprobe since last several years, at least 2 decades. And these are the probes which we have seen, and the difference is that these probes have gases helium, which cool the electronic wire, and when you cool electronic circuitry, you lower the temperature and you improve the conductance. So you have better signals coming out of the same experiment because resistance have been reduced and you get better signal to noise ratio. Then I told you that there were a lot of very brainy, intelligent people over the years have been working on developing software solution for sensitivity. So first and foremost was the pulse NMR spectroscopy, which was developed in early 70s. Lots of people have worked on it. And this was, as we all know, this was a different concept. The definition of NMR was changed altogether. Before that, it was like any spectroscopic technique where you have electromagnetic radiation, in this case, radio frequency. You shine that radio frequency to your sample. Of course, in NMR, you have a magnetic field and then you record the absorption. Pulse NMR spectroscopy has changed the entire theory of NMR spectroscopy. So not only that technique has advanced, but also the fundamental basic concepts have been changed also. And what was the basic concept? That instead of increasing the radio frequency and then having that resonance matching and then absorption, you can excite them all together and then record the relaxation. And this relaxation is non-radiative because the energy which is absorbed by the system when it relaxes back to thermal equilibrium, that energy is released in various forms, including a very weak electric current, AC current, which is recorded by the detector on XY plane, transverse plane, and that is your free induction decay, and that you can do that multiple times in a very short duration. As a result of it, you get lots of spectrum in very short duration, which help you to improve signal to noise ratio. Phenomenal development in NMR spectroscopy. You also know that pulse NMR spectroscopy combined with the vector diagram for understanding now help you to design various techniques which was not possible in conventional or continuous wave. Over there was just an absorption. Now you know that you have net magnetization vector, that you give a pulse, you rotate it in any place on XY plane, and then eventually you can play with it. And that made NMR spectroscopy extremely strong because now you can design your own experiments, you can play with it, you can play with protons, carbon, nitrogen, whatever the elements you have in your molecules independently and together. So, this was mentioned about data manipulation. We'll discuss at some point of time. Not so important. It's more of a mathematical process through which you can help in processing of data and get a better data processing, better uh, signal to noise ratio. There was a very important development of polarization transfer. That was just absolutely phenomenal. Someone says, if the signal is depend on population difference, then why don't we just borrow the population or polarization of a more sensitive nucleus, such as hydrogen, transfer that into insensitive nuclei, and that artificially increase the population difference of insensitive nuclei, so get a better signals. And that took several years before it was technically possible to do that. Theoretically, it was a very simple concept. I gave you the example, but technically it was a bit demanding. How would you do that? What kind of vector diagram, what kind of pulse sequences are required? And so polarization transfer was a phenomenal development. Again, an extremely important milestone which redefined, recalibrated NMR spectroscopy, and also, reverse of polarization transfer, which is called inverse polarization transfer, was developed, and that we would study also. Nuclear overhauser effect is also a polarization transfer, but is for through space coupling. The polarization transfer, which we have studied last time, was a scalar coupling. And that we will discuss again for a while. And also there are chemical method in which you use relaxation reagents such as samarium complexes or other complexes. You add them and they help to relax your nuclei. You get a better signal, improved FID or whatever. So I said that now big machines are available. This is an old slide in 2019, 2021, 1.2 gigahertz was installed, and now there are several machines in the world. There are about 25 Tesla machines 25.2 to be precise, 1.2 gigahertz is 25.2 Tesla machines are now available, and sorry, 28.2 Tesla machines are now available. Ultra shielded, extremely expensive machines, cryopro we have discussed. Now, the last time we have started discussing about polarization transfer, and there was a very simple thing which we have begun with, that sensitive nuclei such as proton, when coupled, scalarly coupled with C13 or nitrogen 15, is possible to transfer the polarization from sensitive nuclei to insensitive nuclei, provided that they are coupled, So that is scalar coupling. And, we explained, I explained, and in fact, I got my coordinator Yahya and Amina help to explain what happened. So in uncoupled system, there is absolutely no interaction between them because they are not neighbors, they're far away from each other, they are not interacting. But coupled system, we all know that the uh, uh, the magnetic power of one nucleus which is connected to other nucleus is affected by the neighbor. So we know that carbon is connected with proton would have effect of the neighbor's orientation. We know that CH is going to be a doublet, CH2 is going to be a triplet, CH3 is going to be quartet. We have taken the example of CH, proton and carbon, who are coupled to each other, and then we created this map. And both of my very able students have actually explained to us that they exist 4 different energy states in which both carbon and hydrogen are aligned to the magnetic field, opposed to the magnetic field. One is opposed, one is aligned, and the other combination also. So I need a green tea, please. Uh, So, for instance, this is carbon transition. So you see alpha in this state. So carbon transition, so alpha become beta, proton remain alpha. This is also a carbon transition in which alpha become beta and proton remain the same. Proton also is affected. So remember that we are talking about proton as a doublet and carbon as a doublet. And proton is affected by carbon. Carbon is affected by proton because both are neighbor to each other. So proton transition in which proton alpha become beta, proton transition from this is two part of the doublets. Remember that the doublet represent two peaks and two peaks because if it is proton, then proton see carbon as up and down. Similarly, carbon see proton as up and down, and therefore combination also. We then translated the same diagram into arrows as vectors. So aligned to the magnetic field, opposed to the magnetic field, one opposed, one, okay, one opposed, one aligned, other opposed, other aligned. This is the magnetic field direction. Then I said, okay, why don't we just, since these are spin half nuclei, why don't we just represent them by plus half H plus half C minus half H minus half C plus half H, and it become bit more complicated. So we added in them uh, plus half, and we add them, become a full integer. So we see plus delta C plus delta H, and similarly. And then, we replace them with numbers just for, so, kindly remember that this is just to explain how polarization transfer work. And if you see the population difference, then for proton signal is 4 and 4. In carbon signal, when you transfer by a selective pulse population from this to this, then the difference become, normally it is 1 and 1, but if you do that, then you get a situation in which you have +5 and -3. So you get a distorted signal. So this was very well understood. And now we have, instead of 1:1 doublet, we have a distorted doublet in which we have +5 and -3. That amplify the signal. That amplification of signal is exactly desirable. This is what you really want to have. Your sample is exactly the same, the machine is same. What you have done, that you have given a selective population inversion pulse. As a result of it, the signal for C13 has increased in size, amplification, and that instead of 1:1 is now +5, 4 times higher, and -3 means 4 times down there. So this amplification is called uh, polarization transfer, and polarization transfer provide you signal like this. So coupled C13 will give you a doublet, very small, 1:1. Decoupled will give you a cumulatively. Thank you very much. Cumulatively, together these combine, and uh, after polarization transfer, you get a +5 and -3. So you get an amplification of signal. Now there are many refocusing techniques available in which you can have distortionless enhancement, and you can see the same refocus signal. And then at some point of time, I also tried to explain that since here we are talking about a scalar coupling, and we wish to only see the improvement in the signal intensity of carbon. We detect carbon only, but we need to play with proton also. If we don't play with proton, how would we increase the intensity of carbon? So this is the reason why we have explained that. I told you that you give a 90x pulse uh, and proton, which is coupled with C13, will split as a doublet. At some point of time, you give a 180 pulse, and this is a spin echo pulse. Remember this, in the spin echo pulse with the sole objective of removing the magnetic inhomogeneity, and also to refocus the coupling. Remember that such experiments, which are longer experiments, refocusing by spin echo is absolutely required. But then you give a 90 pulse. When you give a 90 pulse to this go up and down. So you see that a part of the doublet goes up and the part of the doublet goes down. This is called polarization transfer pulse, because this is the pulse which transfer the population to this. So you see, after 180 pulse, there was nothing on the plus that direction, but that part of the doublet is now added. This is exactly what you have seen in the diagram, population diagram. So there was a population difference, and there were many, many experiments developed. INEPT was the first one. INEPT is called insensitive nuclei enhancement by polarization transfer. Then inept was improved, and we got depth, which is distortionless enhancement by polarization transfer, is essentially the same experiment. The difference is that you carry out some kind of APT with that attached proton test, and then you get polarization transfer based enhancement. So you see, uh, this is carbon-13 NMR, in which you get a signal. You cannot recognize between any one of them. You don't know which one is C13, which one is CH, which one is CH2, and which one is quatri. When you record, this is not polarization transfer. When you record polarization transfer, you don't see quatri carbon. So very obvious that quatri carbon would not really be seen in such experiment. You know that polarization transfer is taking place from proton to carbon. So if a carbon doesn't contain any proton, you don't see any polarization transfer. So in all polarization transfer experiments, quatri carbons are not seen, so they are gone out of the canvas. But by defining the angles, you can distinguish between the CH2s and CHs. Now you can distinguish between, with depth, you can have CHs, CH2s, CH3s, and quatri carbon. It's called A depth. So a new routine was developed in which there was a normal C13 decoupled spectrum, and then these three depth experiment, depth 45, which gives all techniques, depth 90, which gives only the CHs, step 35, which gives CHs, and CH2s and CH3. So you can actually distinguish between all four different types of carbon. It's called A depth, audited depth, or audited depth. And then you see this is quatri carbon, which is not visible here. Similarly, this is CH or CH2 or whatever. So you can distinguish them very, very clearly. And through this experiment, you would be able to not only get a sensitivity enhancement, but also by using attached proton test, which I showed you like this. You remember this, which we have discussed, attached proton test, you can get a different orientation or phases of different multiplicities. I want to, I would like to tell you something very interesting. You see, for instance, in these experiments, you're recording carbon-13. But carbon-13 contain information of attached proton. It is quatri-carbon, no attached proton. It is CH, it means there is an attached proton, one attached proton. CH2, there are two attached protons. CH3, it contains three attached protons. So even you have recorded the carbon-13, information of the partner is there. And that we would discuss in two-dimensional NMR spectroscopy, which we will indulge today in discussion. So, simple one-dimensional NMR, so many of them, proton NMR, C13 NMR, depth, these are all 1D experiment. And 1D experiments are generally very simple. You let them relax, you give a pulse, you record. Okay, so if there are 30 experiments, all are same. if there are 500 experiments, they all are same, exactly the same sequence. You just acquire more scanning, and then you have more exactly the same spectrum. And when you combine them together, you just cancel the noise. So one-dimensional single pulse or double pulse or triple pulse experiments, no matter what you do, all experiments are same. So when Dr. Mera record proton NMR or C13 NMR or DEPT or whatever, the scanning, these experiments, 30, 40, 500, 600 are exactly the same, You use exactly the same sequence and you accumulate, collect lots of spectra. And when you accumulate lots of spectra, you improve signal to noise ratio, because always remember, noise are always random and signals are always at the same place. So this is the sequence of one-dimensional NMR experiments. You carry out certain pulses, exactly same for all experiment. You record FID, you carry out Fourier transformation, and you get a frequency domain signal. And there are so many of these very important one-dimensional NMR experiment. Generally, you always start from one-dimensional experiment. You generally don't go to two-dimensional experiments to begin with. Proton NMR, C13 NMR, various decoupling experiments, attached proton experiments, polarization transfer, inadequate, that we will discuss in a while. All these experiments are one-dimensional experiments. One-dimensional experiment, why they call one-dimensional experiment? Because in NMR spectroscopy, dimension is a frequency. Okay, there is one frequency on x-axis. Okay, so all one-dimensional experiment have one frequency scale, and therefore they call one-dimensional experiment. But then somewhere, somehow, when biochemists thought of using NMR spectroscopy for their work, remember that proton NMR spectroscopy was developed by physicists, first used by organic chemists in liquid phase, generally for small molecules. It was all okay, though because of the insensitivity and low natural abundance of C13, many development were made for sensitivity enhancement, including polarization transfer, pulsing, etc. Biochemists were not really interested. They were not really interested in NMR spectroscopy. It was only back in late 70s and early 80s when they saw that NMR can be used for protein, and they jump into the field. They start recording NMR experiments of proteins, and they saw something like this. Okay, so you see between 1 to 10 or 12, even for C13 of a protein would also be between 0 to 200. There was so much of these crowding, so much of overlapping, so much of these signals. All the informations are here. I bet that all information about the number of protons, about couplings, about chemical shifts are there in these spectra. So they saw something like this and they got absolutely furious. And they says this is non-interpretable, you know. Interpretation is a challenge now. Interpretation, how to interpret such signals. And, there was someone from Caltech, his name was Jenner, Jenner, 1979. He presented a research paper in an NMR conference in California, Riverside. He said it's possible to add one more frequency here. So remember, this is one dimensional because this is one frequency. And he said this is possible to add one more frequency dimension here and pull out these signals on the other dimension, as if you just stretch it to the other dimension. Okay, this is what he presented. Nobody at that time understood what he meant, but everybody understood there was a need of developing techniques which help in the interpretation of these complex spectrum, particularly in the field of biomolecules such as proteins or nucleotides and others. So, and I often give you example. You see overlapping of the signal. It's just like if you are standing in front of mountains and you are on a ground level. I have seen this. I remember some of my students took me to this fascinating place where three mountain range in Gilgit. Between Gilgit and Skardu, there are three mountain range merge, Karakoram, Rakaposhi, and Himalaya. And you stand there on the ground and you see these mountains, beautiful mountains in front of you. And you see them in one dimension because you see mountain in front of you and then you see a higher mountain behind it, just a tip of it, and then, maybe many more which you don't see. Okay, this is exactly what you see in this photon NMR spectrum also, because your visual perception is one dimension. But assume that I take a helicopter, I go up on the mountains, uh, and then I see them from the above, top down. I would be able to see these mountains clearly. Now they'll not really appear like this, they'll appear as round, and I would be able to see how many mountains are there in that mountain range, one after the other, because there are so many of these hills and mountains, one behind the other. So, by going up, you add a dimension, and that dimension enable you to see these overlapping mountains. Exactly the same Gina wanted to present, and for that thing to happen, a new type of NMR spectroscopy was invented, which is called two-dimensional NMR spectroscopy. Okay, so two-dimensional NMR spectroscopy, very obvious that we're talking about two frequency domain, because in NMR spectroscopy, dimension is not integration, dimension is only frequency, okay? Three-dimensional means three frequencies, but kindly remember, there are also time, it's called temporal, but right now I don't want to confuse you with that. There are NMR techniques developed in which people study dynamics in the dimension of time, but that is a different domain altogether. Right now, we're talking about frequency dimension. So one dimensional, as we have explained, one pulse, one detection is called T2. It's very interesting. Kindly remember that now I'm going to talk about small t's, not big T. Remember big T, T1? Big T1 is relaxation time in lattice, spin lattice relaxation. Big T2, capital T2, spin relaxation. Forget that at this point of time. Now we're talking about T times, detection time, FID, reduction decay. And we use the word T2 because somewhere we need to discuss T1. We record Friedek, this is the FID, and this time is then converted into frequency by Fourier transformation. So two-dimensional NMR experiments are slightly different time frame. You of course prepare, you give your signals, you excite them to XY plane, you convert your longitudinal net magnetization vector, you bring them on the XY plane, and you let them evolve on XY plane, okay? You know that when you bring magnetization vector on XY plane, they will not be there forever at the same condition. They're going to split, they're going to move away from each other, they will evolve on XY plane, and they will eventually go up. So your detector will see them as they move angularly with their Larmor frequencies, with the influence of couplings, and then FID would be recorded. In this case, you give them an evolution time. Each experiment is different. So if there are 10 experiments, each is different from the other by incremented. Incremented means increase in a particular fixed period. So by incremented evolution period. Can you hear me? Am I online?
Yes, sir, you're audible. Yes.
Okay, my apologies because sometimes I just keep giving lectures and I'm offline. Okay, no problem. And then there is a mixing period in which they exchange information, then you detect. So of course you detect only one time. It is only T2, but every experiment is going to be different, you know. Evolution time and mixing time are the two times in which spin will talk to each other. If there is cozy, the proton will talk to each other and exchange information about the couplings. If it is heterocozy or heteronuclear experiment like HSQC, HMBC, proton and carbon talk to each other and exchange information. And when you detect this, then you get information about the information exchange. So for instance, this is an experiment. Okay, this is one experiment, second, third, fourth. They're not same. Unlike one-dimensional experiment, they are all different. If there are 10 experiments, 10 are different, but only the T1 time is called evolution time. Evolution time is small t1 time in every experiment is increased. So for instance, if it was 1 second, 2 second here, 3 second here, 4 second here. And remember this 180 is just an spin equipulse, so don't worry about that. Okay, so every experiment is different from each other because there is an evolution time which increase when evolution time increase, every experiment is different from the other because these vectors have moved away. If there was a little time, they only moved away a little bit. If there's more time, then they have moved away far away. So the detection the camera, your detector will detect them at different position in different experiment. Now, I want to give you a very simple example, but a decent analogy. For instance, all of you are protons, carbons, nitrogen, whatever. And your classroom, from one gate to the other, one gate is 90x pulse, which bring you to the classroom XY plane. Okay. And the other gate you exit is a detector where I have a detector, right? So you enter into the class, you are on the XY plane, and then you exit from the other gate, which is the detector. So where I have a sensor or a detector. Let's assume that I give you 1 second to be in the class, and then I ask you to go out. You don't know each other and you have no information about each other, but in 1 second, you would be able to have some content of information about each other. For instance, you would know, okay, there are more girls than boys, okay, some piece of information. Then you go out, and then another experiment is conducted in which I allow you to remain on XY plane in the class, let's say about 2 seconds, So in this 2 second, I allow you to, let's say, speak 1 or 2 sentences. Now, when you go out, you would be able to have more information. For instance, you can say, yeah, okay, students are from different places, and some of them are Arabic speaking, some of them are French speaking, some of them are English speaking, etc. Now you have more information, right? And then another experiment in which I allow you to come. I excite you 90x pulse. I allow you to come into the classroom, and I let you talk for about, let's say, 10 seconds or 15 seconds. And okay, you would have more content information, increased content of information. When I ask you to go out and detect, then you would be able to say, okay, we know that some people are from Yemen, some are from Egypt, some are from Cameroon, some are from that. You have more content information. I have done another experiment, okay? Evolution time increasing. I allow you to stay in the classroom for a longer period of time. Let's say if I allow you to be there for about 10 minutes, and then you would have exactly the information, more information. You say, okay, there are students from different countries. They are Arabic speaking, French speaking, English speaking, Urdu speaking, Pashto speaking, Sindhi speaking, whatever. And then you say, okay, someone is from Sana, someone is from Quetta, someone is from Khairpur, someone is from Punjab, Kashmir, KPK. You have more content of information. So you see, presence of you in the classroom with your XY plane, transverse plane, for increasing evolution time, allow you to have more exchange of information. And if, for instance, I design an experiment in which I don't allow you to speak, I just allow you to see, you would have a different kind of information. If I just bring you inside the class without you being visually able to see each other, you would be able to get information through the voice. And similarly, so I can design experiment of my own choice. I can have homonuclear couplings, I can have heteronuclear couplings, I can have information about through space coupling. I can design experiment as I wish, and I would be able to detect them on the basis of the content of information, evolution time might detect my FID will be different. These FIDs will never be same because FID are information and information are different. In the vector diagram, you can very well imagine that, after evolution time, let's say this one, you see this, you see this, you see this, you see this, then they go on the other side. So you see this so-called evolution. And the frequency spectrum of a signal is like this. Because with time, and they're going up also with time, this is frequency T1, T2, sorry, and these are various spectrum. There's so many spectrums which we have collected with different T1 time. Okay, so you get a pseudo FID. If you make a line on top of it, you get something like this. This is based on T1. Based on evolution, you generated a pseudo FID. This pseudo FID can also be converted into frequency domain and you get a spectrum like this. Okay. So now you have two axes. One frequency axis comes from T2, the other frequency axis comes from T1. T2 is directly detected, T1 is calculated because you already have frequency domain signals, and frequency domain signals are modulated in times, and as a result, you get two frequencies. So you get spectrum like, like this. And this is exactly the theory of two-dimensional advanced spectroscopy. Let me repeat it. With increasing T1 time, the spins on XY plane will exchange information, but this exchange of information is going to be time dependent. You more you time give, the more exchange of information takes place. And that exchange of information is then time dependent. So you created another dimension, and that is the T1 dimension based on evolution. And every FID is different because T1 is different. The FID is different because the content of information is different. As a result, when you convert that through Fourier transformation, in this one simple case of a doublet or whatever, you can see a signal like this. There's so many signals, some up, and then after some time they're going to be down. We created, each one of them is a frequency signal. Remember, these are frequency signal. And each one of them is a separate experiment. And you see they are different from each other. You just put them one after the other. Let's say you have it in plastic sheet. You arrange them in standing manner. You turn on one side, you would be able to see that these frequencies are modulated in T1 time domain, and that you created a pseudo FID. This pseudo FID look like this, okay? And you can convert this FID into a frequency, and now you have two frequencies. One's directly detected from FID T2, the other is indirectly detected through T1, and that T1 is converted into a frequency domain by using the same Fourier transformation, and you get a spectrum like this. So instead of having one-dimensional view, you have a two-dimensional view. What you have done that you have two axes like this, and you stretch the spectrum into the second dimension also. So if you look from the top, because these are not easy to interpret, but if you look from the top, you see them like this. And these contours will tell you about the height of the peak integration. You're not interested of integration because integration you can get very easily from, from one-dimensional spectrum. So a lot of these two-dimensional experiments were designed, an extremely exciting field. Scalar coupling, proton-proton coupling, COSY. Proton-proton coupling in long-range, TOXY. Proton-carbon coupling, multiple quantum. Heteronuclear proton-carbon coupling, proton-carbon coupling. Also, there are two experiments of the same information content. Then you can have HMBC, in which you have proton-carbon coupling in long range. Similarly, you can have NOESY, nuclear overhouse effect spectroscopy, in which you have interaction between two or three or several protons, which are close in space. And there are so many of these experiments were designed. Basic message. During the evolution time, the information exchange takes place. During the evolution time, these nuclei talk to each other. They exchange information. And when they exchange information, when they are detected, their content of information is dependent on evolution time. Remember, more evolution time, more content of information. And you can design the experiment. You can design the experiments that I only want proton-proton coupling. I want proton-carbon coupling. I want proton-proton coupling in space. You can design the experiment by designing the mixing pulses. And then you get these two-dimensional experiments. So anatomy of two-dimensional experiment is this one. If it is two-pulse experiment, T1 increase in every experiment. Remember, every experiment is different. Okay. Don't think of you being a spin. Every time spin start with zero information, but with T1, they get more information, and these T2 is going to be not same for this one. So you can very well imagine that this FID is different from this FID, this FID, this FID, this FID, because nuclear spin have moved away, they have talked to each other, they coupled on XY plane. So these are various experiments. And when you carry out Fourier transformation of this experiment, you get a frequency domain spectrum. You get frequency. We get frequency domain spectrum. So you get so many of these spectrum, but these spectrums are different from each other because of T1 time. And then you combine these spectrum together, you create a pseudo FID, you carry out another Fourier transformation, and you get a second dimension. Remember time. T2 time is a detection time. T1 is the evolution time. Because of evolution time, you get a pseudo FID, and that time is also converted into frequency, and that frequency is now your second dimension. For example, this is proton NMR spectrum of this molecule, So you see CH3, CH2, these protons are here. C13, 1, 2, 3, 4, 5, 6 signals. But if you get the proton 2D NMR spectrum COSY, then you get these three signals as diagonal peak. These are true frequency domain. This is frequency, this is frequency. This is diagonal. And this is off diagonal, away from the diagonal. This off diagonal P are created through the evolution time. This provides you information about the connectivity. So this is proton-proton connectivity. And For instance, this is a very small amino acid valine. So this peak, which is of this is diagonal peak, like NMR spectrum, you're seeing it from above. This connect to this, so you make horizontal peak and perpendicular and vertical peak. Sorry, horizontal line and vertical line. You connect them. So NH is connected to this CH. Very important. In structural biology, the CH is very, very important because that is called alpha proton. This CH is connected to another CH. This CH is connected to two CH3s. So by using the off-diagonal peak, 1, 2, 3, 4, these are just mirror image. Kindly don't take it very seriously. These are mirror images. They are created as a pseudo mirror image in order to distinguish from so-called ghost peaks. So these off-diagonal peak of OFF, off means away from diagonal, off the road, uh, away from the road, off diagonal, away from these diagonal peak. This diagonal peak are nothing but your proton spectrum you're seeing from the above. Off diagonal peak are extremely important because they help provide you additional information. So you get through this two-dimensional cozy spectrum, you can link all these protons together and that help you to interpret. This is what you were looking for. Interpretation was your challenge, right? You, you, you were worried because there was so much information. Now you have really pulled them out into the second dimension. You created a spectrum in which you can use this off-diagonal peak of and then link them together. There's so many other experiments, such as J-resolved, whether you have a J coupling and other experiment also. I think today is good enough for uh, this is an important uh, this is an important lecture. I would be in Karachi on 14th evening and I would be with you on 15th morning to discuss this again, and we will have tea party again, inshallah, and we will discuss two-dimensional experiment. Yahya, Hani, Amina, Lalan, uh, all these bright young girls and boys. If you would like to ask any question to me, I'll be very happy to respond. Where is the mic?
Thank you so much, Dr. for this things. I think today the lecture was so amazing, and I saw myself lost there. But I have one question before you.
I am surprised that you have only one question, Hani.
No, but my question for not this part for the two dimension. I know two dimension needs to read more and more. But about the polarization concept. I have one question about this.
My apologies, I cannot hear you properly. So you speak, then I'll ask Humera to tell me what you are speaking. Because I think there's an echo in the room.
I have a question about
Just ask if you're audible. You're audible. Sir, can you hear him now?
I can hear him now.
My question is the first part about the polarization transmission.
That's my lecture is going on. So just have a seat, please. Miran, how are you? Very well, thank you.
Free now?
Yes, Honey, please. Your question is about polarization transfer.
Yeah, about this part. You say how to do that. When you explain the process, you say first we should to deal with the proton, give it 90 pulse, then a period, then 180 pulse, then period, then again 90 pulse to make all the protons back again to the Z axis. Then this phenomena will happen, the polarization transmission between proton and carbon. My question, why we need this process? As after we applied the P node at the high magnetic field, all the protons and the carbon 13 will be in the same axis, and they can do that polarization transmission. Why we need to deal with the proton for all this, this process about deal with the proton, then when they back, its polarization will take habit. I hope you understand me. Thank you so much.
Thank you very much. Very elegant question. What is the need of polarization transfer when you have very strong magnets? You see, of course, you keep developing stronger and more stronger NMR spectrometers, and you increase sensitivity directly by using strong hardware. But you see, that is not sufficient at all. C13 remain a very, very insensitive nucleus. You always would have a situation in which you will not have more than a nanogram of a sample. You would have scientists working in the field of structural biology with literally thousands of carbons in a very small quantity of sample, right? Remember, the Avogadro number of a protein is different from a small molecule. So you can imagine that in small quantity of protein, you would have lesser number of molecules. And as a result of it, you would always have a challenge of detecting these insensitive nuclei. Nitrogen is a major problem also. You know, when biochemists got interested in NMR spectroscopy, their interest was not only in proton and carbon, their interest was also in nitrogen. And nitrogen, as you know, 10 times weaker magnet, gyromagnetic ratio of nitrogen is 10 times less than hydrogen. Nitrogen is also 0.36 or 0.4 naturally abundant, N15. So you always would have a situation in which, despite extremely expensive hardware, sensitivity would always be a challenge. On top of it, think of it that not everyone is capable of investing millions of dollars of buying large machines. So you don't want to rely only on stronger magnets, because stronger magnets come with a cost. Price tag is very, very high. So there was a solution partly came from polarization transfer, and that polarization transfer experiment was not based on hardware. On the same spectrometer, by using a particular pulse sequence, you can temporarily transfer the polarization or population. Remember, polarization is population. polarization and population are proportional to each other. Polarization, we call it because we talk about magnetic magnets, so we talk about poles. But it is actually a population. There is a population difference. The population difference of C13 is much lower than population difference of proton. Proton has a larger population difference and much more natural abundance, nearly 100%. So if we can temporarily transfer the population or polarization to C13 or N15, you get an enhanced signal of C13 and in N15. And that enhanced signal partly solve your sensitivity problem. It doesn't really make your sample number of carbon increase, So you're not increasing the number of carbon, nothing happened to your sample. Your sample remain the same, you just created a trick. And this trick is very simple that you have designed a pulse sequence in which for a moment the population of proton is transferred to C13 and come back. And during the time, you record C13 as you've seen in INEP, it has an amplified signal. And when it has an amplified signal, this is exactly you want, right? So instead of 1:1, which is a tiny small signal, if we get a 4 times stronger signal, you should be a happy person, right? So this is the objective of polarization transfer. It was explained by two methods, by energy diagram and by vector diagram. Energy diagram was a very simple one in which you could just have seen that if you move from one to the other, the population difference numbers increases also. Vector diagram was a bit harder for you to understand, and we completely understand this is not really something which can be linearly explained, but this is one way of explaining it, that how to transfer the proton polarization transfer to the carbon one. And that has had a huge impact in overall landscape of NMR spectroscopy, because now it's possible for a small quantity of sample to record C13 or N15 or do a lot of structural biology. Any more questions? I think there is in the chat box also, there is a
Yes,
question.
sir. The first question is, what is the number of carbon that can be determined or seen by one proton in structure elucidation?
Okay, so you can, you see, polarization transfer from proton to carbon, right? So every carbon which has a proton will be able to receive polarization transfer. Now it's very obvious that more proton, more polarization transfer. Okay. So each carbon which has a coupling partner, a proton, or each nitrogen 15 which has a coupling partner proton will receive polarization from proton. And as a result, you get the signal. And now how many number of carbons? You can have, very large number. You can have samples with thousands of carbons and all that. But always kindly remember that when you have a large molecule, whenever you have a large molecule, the number of molecules would be less. So because in the same quantity of a sample, let's say 1 milligram of a protein and 1 milligram of cholesterol, the number of molecules would not be the same. You know this, right? Avogadro number. You know this, right? Okay, so therefore, more the sample you have, the better resolution you would have. Okay, the better sensitivity you have. Problem is that in liquid state NMR spectroscopy, no matter how much sample you have, you can only dissolve a certain amount of sample, because over and above that, you would have a problem of a supersaturation and undissolved particles.
Okay, sir, there is another question that a student is asking. I'm currently working on fibril forming proteins and want to analyze the protein as well as fibrils on NMR. Can you tell the details about this?
Humera, can you educate me what fibril means?
So fibril means kind of aggregation. I mean, protein molecules together making some kind of thread-like structures
Okay, so
or kind of aggregation. Yeah.
as in beta amyloid or
Yes, yes, beta amyloid.
okay. So always remember that you can either have a liquid sample or you can have 100% solid sample, nothing in between. Okay, NMR can detect either only purely 100% soluble sample or 100% solid sample. Okay, so if you wish to have a completely dissolved protein, you get spectrum of dissolved protein. If you have fibrils or fibers of beta amyloid protein, then you can use solid phase, solid state magic angle spinning NMR spectroscopy, which is altogether a different domain. I think somewhere at the end, we will discuss about solid state magical angle. So you cannot really analyze them together. You need to analyze them one in liquid phase, the other in solid phase. Any undissolved particle in your liquid solution will make NMR spectrum useless, because then T1 is going to be very high.
Thank you, sir. Do you have any other question? Yes, you can come here. Come quickly.
Thank you very much, Prof, for the insightful lecture. It simplifies the concept of proton NMR carbon 13 and 2D. And I want to use this opportunity to also understand the concept that I just accept as a fact, but I do not really have the understanding of the basis. The proton on the hydroxy group or the hydroxy proton appears in NMR spectra oftentimes as a broad peak. So if I use pyridine, I'll be able to see the OH, the proton. So I do not exactly understand why the peak appears broad. So I'll be glad if you can give me an insight. Thank you, sir.
Okay, thank you very much. Very interesting question. All questions are very, very interesting, to be honest. Okay, so protons are often appear as a broad singlet or no signal, right? Hydroxys. If you try to get, if you're recording the proton NMR spectrum of an hydroxy containing compound in deuterated solvent, exchangeable deuterated solvents such as methanol, CD3OD, right? Then all protons of hydroxy group would be exchanged with deuterium, and you would have no signal. Hydroxy would be completely invisible. You would not see any signal because protons are not there. Protons are exchanged with deuterium, right? But if you're trying to record the spectra, proton NMR spectrum of a hydroxy containing compound, such as ethanol, as in neat or in deuterated solvent which is non-exchangeable, such as acetone or CDT, chloroform or DMSO or something like this, you would not have any exchange. So you would really see the peak of hydroxyl group. But the problem is that it's not a problem. I think it's just a basic fundamental concept that hydroxyl groups, in molecule, there is an intermolecular exchange of protons between two hydroxyl groups. So many of these molecules exchange this hydroxyl group, this alcoholic hydroxyl group will exchange these protons between each other because these are polar partially, and you would also have in hydrogen bonding, right? In such situation, hydrogen is not at a fixed position. When it's not at a fixed position, it will appear as a broad peak. Okay? So imagine that Mahmoud and Adil, again my examples, they have one ball and there is a proton, right? And they are two hydroxyl, they are exchanging this ball, they're throwing away and they're playing with that ball, so this hydrogen is going to Adil and then this hydrogen is coming to Mahmoud and vice versa. As a result of it, proton, the NMR spectrum will detect that as an average, time average, it's not in one position. It is at different position. As a result of it, there's so many positions which appear as a broad peak, okay? Which appear as a broad peak. So broad peak is because of hydrogen burning as well as exchange of protons between the hydroxyl groups. I think there is one in chat box also.
So there is another question that is sample, for example, 5 mg, what quantity will actually contribute to carbon NMR signal since only about 1% is C13? Is it just the fraction of molecules that have all carbon C13?
Okay, again, a very interesting question. Number one, that you cannot really define, to be honest, 5 milligram or 2 milligram or 3 milligram. Always remember that although C13 is only 1.1%, but possibility of C13 at every position of the molecule is equal. For instance, cholesterol. In a cholesterol, this 1% C13 can be of any of any of these carbons. All of these carbons would have C13. No, 1% chance that all 30 carbon or 25 carbons would have a C13. Remember, so it depends on the molecular size. If it is a small molecule, a small quantity of sample is fine. It depends on the kind of a spectrometer you are using. If you are using a strong field, strong magnet such as 600, you can record it in a milligram. If you are using 800 megahertz NMR equipment, you can record your C13 nicely in 0.5 milligram. If Humera allow you to have more skeins, then you can have a better spectrum. So it depends on so many other factors. You cannot really define the actual quantity of the sample. More the better. You have more sample is always better, right?
Any other question? No, sir, there are no more questions. Okay, come Amna.
Assalamualaikum, sir.
Walaikum salam.
Sir, I have one question about Cousy experiment. If I understand right, Cousy experiment is relation between proton and proton interaction, yeah? And see the space between them. So if the proton is too much coupled we will also use Cozy experiment or not? This is my question. I have also one extra information. I don't know if my extract of information is right or not for Hani question. When Hani asked about polarization transfer, why we use it if already the magnetic field is high? Actually, in the previous lecture also I asked myself this question because already if we increase the magnetic field, maybe the thing will change because we told we will increase the sensitivity of our NMR. So when I search about that, there is just simple formula says the population difference equal the magnetic field multiply by your natural abundance. So whenever your natural abundance is there, whenever you increase your magnetic field, still your natural abundance is low. So the population difference still will be also low. If you have carbon, nitrogen, and carbon. I guess nitrogen is less natural abundant, so it will be low correlation. So it will be the number, for example, 0.1, point something, or point minus something. Carbon will be 1 point something. Proton is already high. So if we multiply by the same magnetic field, if it's high, still the proton will give the high population difference and the nitrogen will give the low. That means they increase just in linearity. It will not increase the transfer of the polarization of the population. So they transfer the population difference or increase the population because of that.
My question was,
right?
Okay, both of them, carbon and this proton,
Uh-huh.
the same now in the phenol. Why we need to ask this proton to go this way and back, and I will measure them in the same position here.
Yeah.
The process to make this polarization translation, to make this proton 90 bucks, 80 bucks, 90 bucks again here, go and back. And I will measure here and this is my work.
Still
When you give bars, mean it will move with the same
same
velocity, meaning
Yeah.
too much
or much
to
velocity.
make it moving with the same velocity of carbon. Then if there's some velocity, they will transfer. If it is in the same position, they are different velocity. But now rate of precision of carbon and proton after bites will be the same. Then will transfer from carbon to sorry from boron to carbon. Otherwise, we cannot transfer from H to Z. But after the discuss, they will do the same rate. After that, we will transfer.
Repeat that. Okay, Yahya already answered the question again for Hani, so I guess it's clear now.
No, I was actually thinking before this Middle Eastern conflict convert into a war. This intra-Arab conflict become a war between two countries, Yemen and Sudan. I wanted to intervene. I think we have all responded to each other's question. Let me just give you my insight. I'm so absolutely delighted that we have, good quality interaction with each other, and we are all trying to understand a very difficult concept. Number one, that two-dimensional NMR spectrum spectroscopy is not only proton-proton. It is from proton-nitrogen, proton-carbon, direct scalar coupling, long-range scalar coupling. It can be between proton and carbon in long range. It can be through space. So there's so many of these experiments. Literally hundreds of these experiments are available. And the difference between all of them is a slight vector diagram, which make them to exchange information about a specific type of information. Exactly as if I tell you, I don't let you see each other, you just get information only by speaking. Or if I develop an experiment in which I don't really allow you to speak, but just to see each other. you would have a different content of information. So, experiments are designed in a way that various different kinds of informations are exchanged, and there are so many of these. Polarization transfer, Hani has already explained that, and Yahi has explained as well, that, natural abundance and applied magnetic field remain the same. You just bring polarization transfer and you increase the sensitivity of the signal.
Okay, so there is one last question in the chat box that I have isolated a pure compound, which is crystal form from plant. What is the chemistry behind when compared with other which are powder in form during structure elucidation? So he is a pure compound from plant. And difference between a crystal form and a powder form compound.
Okay, so very briefly, I don't want to take much of your time. I know that you all have other engagements there. So crystallization is a purity phenomena. If you get a compound in crystal, it means there's a pure compound, right? So if you get a crystal, the best method for you, and if it is really serious, genuine, good, unknown compound, you go for X-ray diffraction. If you want to go for NMR spectroscopy, majority of the laboratories are conducting solution phase NMR, liquid phase NMR. There are hardly any lab. We don't have it. I was trying to purchase solid state probe, but that solid state probe can handle crystals. So there is NMR based crystallography also. But that's a different domain altogether. There is solid state magic angle spinning. So your crystal, you need to dissolve it in deuterated solvent, you get NMR.
So there is another question. So please, can you explain briefly on the use of relaxing reagent in enhancing sensitivity of NMR spectroscopy?
Okay, very brainy, very interesting question, like all others. You see, what I used to do when I was a student, I realized that many C13s is a problem with the C13 also, especially cautery carbon. They don't have any mechanism, not a very effective mechanism of relaxation. And that is the reason cautery carbon appears very small. There is genuine carbon, but their integration is not similar to CH3 carbon. Remember that in C13, integration is not reliable. Integration is not like proton. One proton is equivalent to one proton, you get the same integration. In C13, CH3, CH2's quaternary carbon can be different depending on their relaxation time. So if you add a small quantity of relaxation reagents, and I can provide you the list of relaxation reagent, very small quantity, just add into it. This relaxation reagent absorb energy and help this quaternary carbon to relax. When they relax, you get an FID, you get a better signal. Okay.
Sir, can we characterize by NMR complex X conjugated compounds such as mastoperin, gold nanoparticles, ssDNA aptamer? Can we do them with NMR?
Again, a very important question. You see, metal complexes, if they are soluble, you only get proton part of it. You don't see metal. You can record proton NMR. And if you have an organometallic complex, and you have, for instance, an organic ligand and a metal, before and after, before coordination and after coordination, there is going to be a chemical shift difference. And that help you to analyze whether this complex has formed or not. Because when it's complex form, metal are extremely electron donating. So in metal complexes, the organic or molecule, which is a ligand, will go into the negative below zero. So you can analyze them, but of course you will not be able to see except what you are trying to see, either proton or carbon. Metal, you can only guess indirectly. You can only guess indirectly which part of your metal ligand chelated or coordinate, which part of your organic ligand has chelated or coordinated with the metal, settled metal.
Okay, sir. All questions are answered.
Thank you very much, everyone, and see you inshallah next week. Assalamu alaikum wa rahmatullah.